Now we start with the steady state error for state space system. In this we will study two methods. Method 1, determination of steady state error for state space system. Method 2, determination of steady state error for state space system without determining the inverse of Si minus A. In classical approach, we have seen the calculation of steady state error for type 0, type 1, type 2. So, why there is need to calculate the steady state error? Suppose if you take classical example or classical control plant GS, and now here is a feedback RS into YS. So, our basic purpose that we are giving the input, that is RS, that is the desired, and we are getting for the system we are getting Y of S, and we are checking the response as we are applied input is like this, and if you getting response like this, and then we are saying that there is a steady state error, this is error. Sometimes if you apply input step input and we get like this, so we say that there is no error. So, for any plant we have apply input getting output, we are saying whether there is error or not, but why we are doing all these things? Because my desired aim is important. In control system we have some desired aim, desired input or desired output we want. Okay, so the desired output we have fixed first, and then we see the plant which is from the plant we are getting a desired output or not, and if we are not getting a desired output, then what we are doing? We are designing the controller. That means here also in a classical control system we are designing controller, and here this particular part, if you see this part, we use a controller C of S. This C of S can be also be in the feedback path also if required. So, that means the calculation of steady state error is very much important. But now we are working on advanced linear control systems, that is working on a state space system, and whenever state space, definitely final aim is to design a controller, and if you cannot calculate the error, it means that our controller design may not be so useful. Therefore, we have to calculate the steady state error for a state space model. Now, we will see how to calculate the steady state error for a state space system. So, now we write a state space system and assume that it is in closed loop form. So, now the consider the closed loop system as x dot equal to ax plus bu, y equal to cx. Now, we have plant GS, this plant, and if you take y of s, Ys by Rs equal to Gs upon 1 plus Gs. There is a closed loop plant, that is Ys by Rs equals to closed loop system. There is Ys by Rs, Gs upon 1 plus Gs Hs. Hs we have taken 1, so it is negative feedback, and this we can write down as T of S, closed loop transfer function. Now, here same thing we can write down Y of S Rs equal to Gs upon 1 plus Gs, and this can be written as Y of S equal to Gs upon 1 plus G of S into R of S, and then this Y of S, as I told, Gs 1 plus Gs, it can be Ts, so it is T of S into R of S. This is the first equation which we got. Ys equal to Ts into Rs. Now, our purpose is to get the steady state error, that is our purpose is to get the E of S. So, how do you write this E of S? This E of S equal to reference input, that is R of S minus Y of S, and Y of S we have already calculated. So, just shifting this Y of S here or placing this Y of S here, we will get R of S minus T of S into R of S. Now, this R of S is there, so we can take it common. R of S 1 minus T of S. Now, we have got the equation like this. In earlier classes, we have seen the conversion of the given transfer function into state space, even state space into transfer functions. But now, here our input is not numerator and denominator. Here our input is A, B, C and T. Here T of S is written in terms of GS, which is a part of the classical. Therefore, what we can do, this Ts we replace in terms of A, B, C, D matrix. So, how do you replace? So, here R of S Ts, so that can be written as C Si A inverse B, assume that D is 0. That is, we have seen that any transfer function G of S, now this, that is 1 plus G of S, that is T of S, that is a transfer function. Actually, when last time we have taken this example, we have written in terms of G of S, that is C Si A inverse B plus D. Now, here this is GS transfer function, so TS is also transfer function. So, here T of S is written in the same way, C Si A inverse B. So, this is like this. Now, we have got E of S, but we have to determine the response, and the response in the time domain, that is Y of t like this. So, therefore, everything this Y of t, E of S, R of S, it is in terms of R of t, E of t, Y of t. So, here also E of S we can write down in terms of E of t. Now, how to get it? So, here we can use the concept of the final value theorem. Therefore, this limit t tend to infinity E of t equal to limit s tend to 0 of S into E of S, and finally, this can be written as limit s tend to 0 of S into R of S 1 minus C Si minus A inverse B, that is steady state error is like this, that is limit t tending to infinity. Limit t tend to infinity E of t equals to limit s tend to 0 of S R S 1 plus C Si A inverse B. Now, why we are taking t tend to infinity? Because in time domain steady state mean at t tend to infinity, that is time is infinite, that means when we take the response any plant, this is t. So, when t tend to infinity, that is we are moving at last end state, steady state. Earlier part is the transient part. So, here main aim is to determine the steady state error at t tend to infinity, that is at steady state what is your output. So, this is the formula for getting the steady state error, limit t tend to infinity of s tend to 0 as R of S 1 C Si inverse B, and you will find that this error is depend upon what input we have, and again this C Si inverse B. So, now this we have determined, that is E of t we have determined. But here we will also again observe that here we have to calculate Si inverse, and also we have seen that again to calculate Si inverse sometimes difficult, that is why we are going for the Lagrange algorithm. So, here also we can use the Lagrange algorithm, and you will see that in all the techniques we have studied earlier, this Si inverse and inverse plays a very much important role. But now, now our aim is that can it possible that we can eliminate to calculate the Si minus A inverse. So, partially we can do it, that is now we will develop a method, or we can solve a problem example in a such a manner that there is no need to calculate the inverse of Si minus A. That is, our aim is that to eliminate the use of Si minus A inverse partially. That is, our aim is that we have to calculate only A inverse in getting the steady state error. Can it possible? That is, our aim is, can we get E of t without calculating Si minus A inverse? So, this is possible. So, we can see this method. So, method 2, determination of steady state error for state space system without determining the inverse of Si minus A. Now, here this method is explaining. So, we will find that here also we need to get the inverse, but it is not Si minus A. Here in this method only there is need to get the inverse, that is A inverse only. This part Si part we can remove. Now, we will see this method. So, now steady state error, so without determining the Si minus A. Now, we take the same plant, x dot equal to Ax plus Bu, y equal to Cx. Now, we have a steady state, because steady state is required. So, here the steady state means x S of s, we can write down as x x1, x x2, x Sn, that can be written as x into S. That means, when we are saying that at t into infinity our states will also reach a steady state. So, here all this state information we have written x S1, x S2, x Sn. So, we can write down as this as also xx, this SS or xs also, there is no any issue. Now, here when state are a steady state, definitely they will also constant. Therefore, where this x S I, where I varies from 1 to n are constant, they are constant. So, when they are constant, these are constant, if you take the differentiation of this, what will happen? We can write down as x SS dot equal to 0. So, we can write down as x S dot A x SS plus B into U, y equals to C x S S. Now, this particular equation is nothing but the steady state equation of a state space model. Here x s is 0, but steady state derivative of steady state is always 0. Just see here, if you take any response, if response is like this transient and finally steady state, so this is a constant. So, derivative of constant becomes 0. So, here also x s dot equals to 0, we got x dot equals to 0. And now, about the input. So, input is here, input, let us say u equals to r equals to 1, that is unit step. Now, here we are concerned with the unit step input, steady state equation, and then we will see what result we will get. So, now here 0 into A into xs plus B, u is there, that is you have a steady state of 1 and y ss equal to C into xs, that is here unit step input, that is r equals to 1 here, it can be called as a u also. So, y of s is a steady state output, and now if you solve these equations, so what we will get, this is minus a into xs equal to b. So, a minus xs equal to b, as I told you that this x of ss it can be written as xs. Therefore, same thing we have written 0 axs b into r. So, b into 1 step input, that is r equals to 1, and therefore, what will get yss equals to c into xs. Now, here this x of s equals to minus a inverse b. X of s is nothing but minus a inverse b. Now, what is our requirement? We required error at t into infinity. So, here this e raised e of infinity, the reference input is 1. So, 1 minus y ss, steady state error, that is reference input 1 minus y ss of s. This is equation in time domain, and that is why we get r equals to 1. We have solving, we got a x of b, and finally x of s equals to a minus b. Now, this steady state error equals to reference input 1 minus output y s. What is the role of this here? Now, here will come the role of this, because the steady state output. So, I am saying this yss is nothing but your yss to c into xs y of s. And what is xs? This xs nothing but c minus a inverse b, that is minus c a inverse b, and therefore, the steady state error we can write down as e of infinity 1 minus c into xs, that is equals to 1 minus what is cxs equal to minus c a inverse b. So, we can write down it as c xs equals to a inverse b. So, we can write down as 1 plus c a inverse b. So, steady state error 1 plus c a inverse b, and we will find that in this case the steady state error, there is no term of s has come. It completely depends upon c, a and b matrix, and we can directly get the steady state error. So, what advantage we will get? Because advantage is simple, because here we have to use a inverse, but whereas if you see the earlier method, we have to calculate si minus a inverse. So, this part has been removed. So, this we have calculated for step input. Similarly, you can go for ramp input, parabolic input, or for any other input. You can try this approach, and we can get the formula for steady state error. So, this specifically for steady state error for a step input, that is u equals to r, that is sometimes you take input as u, sometimes as r equals to 1, whereas u of s equal to r of s equals to 1 by s. So, here we taken r as 1. So, b into 1 we have got here b, and therefore, we got y minus a of x into b here. Just see this part. And finally, we have got e infinity equals to 1 minus yss, and what is yss? It is cxs, and how to get xs we have got by this, and we are replacing this, we have got this particular. Now, all this methodology we have seen, that is calculation of error. Now, we solve an example based on this, that is we will solve an example by both the method, by method 1 and method 2, and see that whether we are getting the same result or not. Now, we take an example. Let us say this matrix A is written as 0 1 minus 2 minus 3, B matrix as 0 1 and C matrix as 1 0, and this is particularly for your model x dot equal to ax plus bu, y equals to cx. This is the model. And again, one property we have got, this is no d, it means that your, if you convert into a transfer function form, the degree of denominator is greater than the degree of the numerator, that is observations, that is no d is involved. Now, our aim is to calculate the steady state error. So, first of all we use method number 1. So, method 1, method 1. So, method 1, that is steady state error equal to limit s tend to 0 of s into E of s. And what is E of s? We have seen this E of s is equal to R of s 1 minus C SI inverse B, that is E of s equals to R s 1 minus T s. So, we use this formula here, that is E of s equal to R of s 1 minus T of s. Now, this is the plant A, B, C, D. Assume that this plant is in open loop form, that is we have G of s equal to 1 upon s plus 1 s plus 2, that is equal to 1 upon s square plus 3s plus 2, and therefore, this is the particular model. So, this is the GS. Now, here we want Ts, that means we have to determine the closed loop characteristic equations. So, this T of s equal to G of s divided by 1 plus Gs. So, here 1 upon s square plus 3s plus 2 divided by 1 plus s square plus 3s plus 2. So, if you solve it, so what will get? This 1 plus s square plus 3s plus 2 and this will cancel, 1 will remain in the numerator. So, here s square plus 3s plus 2 plus 1, this is 3, that is this is the Ts. So, we will find that particularly open loop for this example with 2, whereas in closed loop this 2 has been increased by 1, this value of the last coefficient has been increased by 1, but this Ts we have to consider, we do not have to consider this because our error is depend upon the Ts. And what is Rs? Rs is the step input, the step input is 1 by s 1 minus, what is Ts? 1 by s square plus 3s plus 3. Now, we have to use final formula this like this ESS. Now, this E of SS equals to limit s tend to 0 of s into E of s, this is the formula. So, now E of s is like this. Now, s we have to multiply and see what result will get. So, here steady state error, that equals to s multiplied by 1 by s 1 minus s square plus 3s plus 3. Now, this s will cancelled. So, we will get 1 minus 1 upon s square plus 3s plus 3. Now, if you solve it, s square plus 3s plus 3, s square plus 3s plus 3 minus 1, this can to 3 minus 1 2. So, s square plus 3s plus 2 divided by s square plus 3s plus 3, and here the steady state error is nothing but this limit s tend to 0, because all this portion is concerned with the limit s tend to 0. So, if you replace s equal to 0, so what will get? 2 by 3. Now, this is the steady state error which we have got for this example when considering the system in a closed loop, and by means of this we have got result. Now, our main purpose is to get the steady state error when or our main purpose is to solve this example by second approach, and we have to see whether we are getting same result or not. Now, the same example we are taking a equal to 0 1 minus 3 minus 3, b 0 1, c is 1 0, a b c. Now, a b c is there, but you will find that the a which we have taken earlier, it is 0 1 minus 2 minus 3, whereas here we are taking a as 0 1 minus 3 minus 3. Why? Because here our main concentration on closed loop plant, that is our model x dot equal to ax plus bu y equals to cx, it must be in a closed loop for using the method 1. That is why here we have shown the state space model for a closed loop plant, that is we have written equation ABCD from Ts, that is A, B, C, and that plant is Gs upon 1 plus Gs. Now we have to use the formula for this is E of infinity equals to 1 plus C A inverse P, this formula to be used. Now here to get the A inverse, we can use the formula for adjoint of A divided by determinant of A. Many times we have seen this particular formula. So here adjoint of A, so A matrix is 0 1 minus 3 minus 3. So adjoint of A, nothing but the transpose of the cofactor, transpose, that is cofactor of A transpose. So here we will get minus 3 0, here we will get 3, you will get minus 1 transpose. So we will get as minus 3 minus 1 3 0, and then the determinant of this. So if you calculate the determinant of this, the determinant will get it as plus 3. So that means the A inverse equal to minus 3 minus 1 3 0, and determinant of this is 0 into minus 3 0. So it is plus 3, and therefore this A inverse, that is equal to here minus 1 by 3 1 0. Now the main purpose is to get calculation of 1 plus C A inverse into B. Here we can solve it like this: E of infinity equal to 1 plus, what is the value of C? C is 1 0. What is A? A can be written as 1 by 3, again same, minus 3 minus 1 3 0 multiplied by, what is B? Is 0 1. So here 1 plus 1 0 multiplied by 1 by 3. Now if you solve this multiplied by this, so you will get minus 1 0. Now here 1 plus 1 by 3, now here 1 0 minus 1 0. So here you will get 1 plus 1 by 3 into minus 1, here 1 minus 1 by 3, you will get 2 by 3. So here we have got the steady state error for this same example, as 2 by 3, and even by classical approach we have got 2 by 3. That means we are getting the same steady state error. So we have to see based on the problem which method to be applied. So here we will find that for a lower order this method is okay, means first method, but as the order increases I think this method will be better. As we have seen the various formulas earlier, that is to get the steady state error, here 1 minus C SI A inverse, that can be used, or simply we can go for the transfer function model of this plant. So sometimes if you having this GS as a plant, for GS, that is we having the numerator and the denominator, then we have to use the concept of this or Laplace, and we have to get this SI minus A inverse. But if you are knowing directly getting the transfer functions, then sometimes this method can be very much useful. So we have to see from the data available to you, based on the available informations, you have to choose the method. Sometimes we cannot say that this is best or this is best, it depends on the which type of example, which type of data is available to you. but the last end of this, that we have to simplify the calculation. So, here we have seen one example, and for using this both this example, we have got the steady state error, and we will see that 2 by 3 by the second method, and here also you will find the steady state error 2 by 3, and here also 2 by 3. So, both the way 2 by 3 and 2 by 3 we have got the result, and this error is very much important in a controller design. So, when we will going for the controller design, controllability, observability, we will see its effect. Now, about the references, particularly you will find that the method 2 which I explained to you will find in these particular books, or some more example you can find here, and here also some more information we can get in Nagraj and BCG. Also there are many books which we can refer, and here only one example I have taken, but similarly you go for the many more example, solve this and see that which method is best, so that you can clarify. Thank you.